Okay, hello everybody. This is the third episode already of the third season. And it's Halloween today, so we have a bit of a spooky topic today, theta models. But luckily we have Nicolas Sarkis to help us out today when because he's presenting how you can compute two isogenies on Kummer lines if you understand these topics very well. He's a PhD student at the Institut de Mathématiques de Bordeaux, and is going. Well, actually, I have nothing to add to this. Floor is yours, Nicolas.
Thank you for the introduction. So, yeah, hello everybody. I'm going to talk about how to compute two isogenies on Kummer lines. This is something I've been working on during my first year of PhD with Razvan and Damien. And so the outline of this talk will be to go to two examples of Kummer lines that are good example of Kummer lines that are classical are Montgomery curves and theta models. So I will first talk about both of these, introduce Montgomery curves, theta models, and then get to the more general framework of Kummer lines and how we can compute two isogenies and find results that were already known and show the more general framework. So let's start with Montgomery curves first. Montgomery curves are, so first, Montgomery curves are elliptic curves. You can always put an elliptic curve in a short various first form, and Montgomery curves have this specific form, and geometrically you can show they look like this when you draw them. So they have this X factor, which is important. And we focus on, in this part on, we focus on Montgomery curves. So how do we define a Kummer lines from a Montgomery curve? First, from the arithmetic law on elliptic curves, you have that if P is a point, you have to think of them projectively, and if a point P is represented as XYZ, then minus P is almost the same, it's X minus YZ. So if you just forget about the sign of Y, you can get a Kummer line by quotienting by plus or minus, identifying P and minus P. And so mathematically, how does this work? It's you have this map pi from E to the projective line, and you send a point XYZ, you forget the Y coordinate, as I said, so you just send XYZ to XZ if you XZ or 0, 1 if you are the point at infinity. And one notation I will be using is the image of a point P. I will denote it in between brackets. So what happens on Kummer lines is that you don't have an addition law anymore. It's not working because if you look at this diagram, if you have P and Q on the Kummer line, you get on the elliptic curve, you get P minus P, Q minus Q. If you add them, if you mix the M to and add them, you can get up to 4, you can get 4 points on the elliptic curve. And if you go back to the Kummer line, you have two classes. You have P plus Q and P minus Q. So you can't really add them. But one thing that happens is that if you know PQ and P minus Q, you can determine which one is P plus Q. So this is called differential addition. And this is what Montgomery introduced in 1997. So you have a differential addition formula, and the thing I won't explain where the formula comes from, but one thing to notice is that you only need XZ of PQ and P minus Q, and you can compute XP plus Q and ZP plus Q with that. And this formula doesn't work with if you have you must have P different from Q. This formula doesn't work in that case, so you have also doubling formulas for the case P equals Q to compute 2 times P. And with that, you can build what's called a Montgomery ladder. It's an algorithm to compute a scalar multiplication. You can chain this algorithm, because if you take 2 points R and S that only differs by P, with one differential addition and one doubling, you can get 2 points that will also differ by P. So on the right side, I have an example. if you want to compute 22 times p, you start with the point p. So first you do a doubling to get 2p. And then you look at the bits of n. So the first bit you will read is 0. So 0 on the Montgomery ladder is differential addition, or you do a differential addition and a doubling on the left point. So from p and 2p, you get 2p and 3p. Then you read 1. So you do the second step of the ladder, get 5p and 6p, etc., 11p, 12p. And in the end, you can get 22p and 23 times p, but we don't mind about that. And it's an efficient way because it's an efficient way to compute the scalar multiplication of a point on an elliptic curve if you only care about the x and z coordinates. And yeah, I will be talking a bit later about how to improve that, but I need to talk about theta models first. So this is for arithmetic on a Montgomery curve. And now about 2 and 4 isogenies on a Montgomery curve. So first about 2 isogenies, you have formulas by Renz. So why do we want to compute 2 isogenies? Because you can, to compute a 2n isogenies, you can just chain n 2 isogenies. So the starting point is how to compute a 2 isogeny. Or you can also recover doubling formulas with 2 isogenies, because if you have an isogeny f and you know its dual f hat, then f hat circ f of p is equals to 2 times p. So that's the two use case of 2 isogenies. And here you have on the screen formulas for 2 isogenies on a Montgomery curve. If you have a 2 torsion point that is not the known one on the Montgomery curve, I did not say that, but a 2 torsion point is a point with y equals 0 on the curve. And because you have this x times x squared plus ax plus 1, you always have a 2 torsion point on the Montgomery curve. But here, if you require another one, which is t, you have efficient formulas to compute a 2 isogeny. So the codomain can be computed in 2 squares, the image is in 4 multiplication and some addition. And the doubling, if you do, and the doubling corresponds to the formula I showed previously on the arithmetic. And one remark is, I did not talk about the complexities, but the computational cost, but there was a M0 to denote the multiplication by a curve constant earlier on the arithmetic. However, when you chain isogenies, you have to compute new codomains. So these curve constants, you lose track if they are small or not. So I will count M0 as 2 multiplication later, because you have to multiply by the numerator and the denominator. And I will not care more about these curve constants. And how do we compute 4 isogenies? You can either chain 2 isogenies, or you can you have also formulas by Costello and Isil for 4 isogenies on Montgomery curves. So I won't go into the details of the formula, but you need an additional 4 torsion point. And in that case, you can compute the codomain, you can compute the images of a point. And the images is in 6 multiplication and 2 square, which is a bit better than 2 times 4 multiplication, because squares tends to be faster than multiplication on a computer. So that's the known results on Montgomery curves. And now I try to detail and introduce you to theta models, how we can do things that will be really similar. And first, why are we doing that? On Montgomery curves, what we did, we had this map from the elliptic curve to the projective line, which had good arithmetic. And another way to get a lot of these maps is to use theta models. Plus, another thing that is nice about theta models is that you can use them in any dimension. You can, in dimension 1, you have lots of coordinates on elliptic curves. In dimension 2, you don't have much. You have less formulas, but you still have some but you still have some, and in higher dimension, starting from 3, you don't have a generic framework to coordinates frameworks. So theta models are useful for that. I won't go into the details of how we know if elliptic curve has a theta model or can be put in Montgomery form or things like that. But we are working on a paper to try to classify elliptic curves which has Montgomery using the Kummer line, so the 4-torsion property on the Kummer line. For instance, Montgomery is the same as having a rational 4-torsion point on the Kummer line, and theta is the same as having 2 independent rational 4-torsion points on the Kummer line. And to introduce theta coordinates, I will work analytically, so over C. And this generalizes as well because we have a Lefschetz principle. And on the complex plane, an elliptic curve is a torus given by some tau in the upper half plane. So now I have to introduce a lot of notations. So first, what is the theta function? You start with a Jacobi theta function. It is this formula. And from that, you can have many more, sorry, you can have many more formulas which are the theta function with characteristic. It's almost the same. You just, the n from the Jacobi function, where you just change them into n plus a over L, and you translate the z by b over L. So you have formulas for this function. We'll see why they work well. What we call a function of level L is functions that satisfy these conditions, and they form a vector space. If you call it R tau L, you have a vector space of L functions, and we know the dimension of this space. It's L. And the sketch of proof, you can find all these details in a Mumford book about theta functions. And one of the proofs is to prove that the dimension is L, is to find some basis based on the theta functions with characteristics. So that's why we need those. And from now on, I will focus on the case L equals 2, because computationally, you don't want to have too many coordinates. So yeah. And for some example of coordinates on what we call theta models, we have the basis I will be using is this one, the theta 0 and theta 1, which are just theta function with specific characteristics. And we call A and B the value at the null point are called the theta constants. And one interesting thing is that also you can define XZ coordinates from Montgomery like we did in the first part, or you can also define them by theta with some theta function, like X is theta, this theta function squared, and this one squared. So it's a first approach to why we will have good conversions between Montgomery and theta. And why we did that is we have a theorem by Lefschetz. If you take a basis of R tau 2, then you have an embedding to the projective line. If you take a point on your elliptic curve up to a sign, sorry. If you take a point on an elliptic curve up to a sign, you can project it on the projective. You can send it to the projective line with this map. And so that's why we want this theta function, because theta function helps you to build bases of R tau. And with basis of R tau, you get maps from elliptic curve to projective line. And what we call the theta model is the special case of the basis theta 0, theta 1. And this is what I denote theta AB, because you only need the theta. You only need the theta constants to describe it fully. Okay, so now that I have one model, theta AB, I can build many more models from that, because what we saw is that to build a theta model, what we called the theta model was just the image of some basis of R tau. So if I already have a basis, I can just change it into another basis, and this will help me build lots of models. So I start with this theta model, which has a theta constants A and B. And from that, you can do first operation, it's the Hadamard transform. You just take the x coordinate and the z coordinate, and you do the addition on one side and the difference on the other side, and it's bijective. So you transform a basis into another basis, and this is what we call the dual model. So you stay on the same curve, but you could also multiply by the theta constants A and B, because these constants are not zero. If you just multiply the x coordinate by A and the z coordinate by B, you still have a basis. So you have a new theta model. This is what we call theta twisted model. And all of this was over the curve E tau, because we kept having basis of R tau. And the last one is a bit special, because this is a theta squared model. You can take the squares, and if you do some computation with the formulas before, it can be seen that x squared and z squared correspond to a basis of R tau over 2. So it's not the same curve. It's on an two isogenous curve, but you have also this theta squared model, which will be useful in the in the next section. And know that you can build a lots of models from this one. You can also chain this operation and relate them that way. So I don't want to detail this diagram. The idea is just to say that starting from the model theta AB, you can do a lot of operation with S, H, and C, and build a lot more models which are lots of relation between them. And you have you just have two main lines. The first line is on the curve E tau, and the second line is on the isogenous curve E tau over 2. So that's it for the definition, I think. Yep. And you have the same background as the one we had earlier in Montgomery curves. You identify plus z and minus z, so you don't really have an addition law, but you have a differential addition law. If you know p, q, and p minus q, you can recover p plus q, so you still have a differential addition formula. Also, there's a typo. The plus 1m should be it should be a big M, so 3m plus 4s plus 1m0. And you also have doubling formulas. The difference with Montgomery arithmetic is that you can put p equals q to get doubling formulas, and this is what we do here. One thing to notice is that it may be better computationally to store the squares. You can, because in the differential addition you have 4 squared to compute, but if you store the square of p and q, of the x and z coordinates of p and q instead of the plane coordinate, you can improve the arithmetic a bit. So that's what I did here. If you call big X the square of the x coordinate and big Z the square of the z coordinate, you get formulas that only use 2 squares instead of 4 squares. So that's a bit better for differential addition, and you don't improve doubling, but you still improve differential addition. And now, how does this compare to Montgomery curves? So we will be working on theta squared because it has better arithmetic in the next slides. How does this compare to Montgomery XZ coordinates? Differential addition, you always add the same thing plus one curve constant multiplication, so it will never be better. But doubling could be better. For instance, if you work on fp squared, and you write it as fp I 1p is equal to 3 mod 4, so that's something used in isogeny-based cryptography. You have a square is about 2/3 of the multiplication, so the doubling should be faster on the theta squared model rather than the Montgomery model. But this also relies on having a small curve constant multiplication. If your curve constants are small and you can multiply by small constant faster than by any number, you can get a better results with theta squared doubling. I have an example after. I first have to explain how to convert between, because the idea we would like to use is, because we have a better differential addition in Montgomery and a better doubling in theta squared, can we convert between them to get the best differential addition and the best doubling? And the answer is yes, we can. So I try to explain this a bit. There is a strong relation between Montgomery curves and theta squared that was already known by Isil and Renz. You have an isomorphism between, if you take this Montgomery curve, so it's a Montgomery curve because you end up, if you do the multiplication, you end up in x squared plus ax plus 1. You just have extra two torsion. And you have an isomorphism between the theta squared model and the Kummer line associated to this curve, given by these formulas. The issue is you have to multiply, to do the conversion from a point in theta to a point in Montgomery, you have to do two multiplication. So that's not ideal. However, something that was already known by Karaty and Sarkar is that in theta squared model, you have this two torsion point 1, 0, and in Montgomery model, you have this one, a squared, b squared. And then you have a bijection, which is way easier than the previous map. Given just from a point theta, if you write it x in theta squared, you just send it to x in Montgomery, and you recover this same point up to a two torsion point. So you send a point in theta to the corresponding point in Montgomery plus a two torsion point, and vice versa. So this conversion is completely free because you just keep the same value, but you have to deal with the two torsion point. And the question is, can this improve doubling? And the answer is yes, because if you because we have two torsion point, 2 times t is equal to 0. So if you start with a Montgomery point, you use the free conversion to theta, you recover the point in theta plus a two torsion point. You do your doubling in theta, and because t is of two torsion, it disappears, so you only have 2 times the point in theta. And then you once again do the last conversion to Montgomery, the free conversion to Montgomery, so you recover 2 times the point in Montgomery form plus a two torsion point. So you can't directly use the ladder as we did earlier, but we have to adapt it. And this is something we've been working on called hybrid ladder. So the algorithm is really similar to what we had in Montgomery ladder. The difference is that instead of having in Montgomery ladder, the difference of points had to be p, but here we allow it to be p or p plus a two torsion point. And the output will be 2 points that will only differ by either p or p plus a two torsion point. And same thing, I have an animation about that. If you want to compute 22 times p, you first do your doubling you use your doubling in theta, so you recover 2 times p plus the two torsion point. And then you do your ladder step. Every time you'll do a doubling, you end up with a two torsion point. And differential addition, it will depend whether you have, here you have p plus 2p plus t, so it's 3p plus t, but next step, the differential addition will be 2p plus t plus 3p plus t, so the t plus t will cancel out, and you recover 5p. And you change that, and at the end, you may have a correction step. You get 22 times p plus a two torsion point, but we know how to deal with that. We know how to convert how to do this translation on Montgomery, and you only have to do this once. The idea is that you don't need to deal with the torsion point until the end, so it's only one step and it doesn't cost much. And we have a proof of concept. I won't detail the context. The idea of the context is just we wanted small constants on our curve, so we did something that enabled us to simulate small constants to get our results. And what we got is that the hybrid ladder got around 6% faster than the Montgomery ladder, so it should work. It's a proof of concept because it's not the context, the usual context, but it should work at least. So that's how you can use this conversion with the two torsion point. You still have a two torsion point sometimes, but it's not a big issue. You only deal with it at the end. And now I will be talking about how to compute two isogenies on theta models, because we've done arithmetic like on Montgomery, so let's do two isogenies like in Montgomery. If you if you work in the complex plane, the two isogeny we're interested in are I send z from the curve E tau to z on the curve E tau over 2. And the dual is you send z on E tau over 2 to 2z on E tau. And what we saw earlier is that when you square the coordinates theta I, when you square the coordinates on a theta model, so corresponding to E tau, you ended on the curve corresponding on the theta squared model corresponding to the curve E tau over 2. So this is the operation that will be our isogeny. And here I took the simplified version of the previous diagram. You can see on the vertical lines you have the two isogenies. And what we want to do is so you only need a square a square corresponds to your two isogeny. But if you start on a theta model, you also want to land on a theta model. And if you start on a theta squared model, you also want to land on a theta squared model. So you have to do some more steps. And this is, so you have, first you do your square, you end up in, if you start in theta, you do your square, you end up in theta squared. And with the following chain of operation, you do an Hadamard transform, then multiply by some constants and do another Hadamard transform. You end up once again in a theta model on the curve E tau over 2. And the cost of such a two isogeny is sorry, 2 multiplication plus 2 square. And same thing, it doesn't change the cost, but if you want to work with a theta squared model, you start on the theta squared model, you do the constant Hadamard first, and then the square at the end. And what I explained on Montgomery curve is that when two isogenies also helps you recover doubling formulas. So instead of going all the way to the end of the isogeny, you could choose when it's split at the S and H at the end, you can choose to not do the Hadamard transform, but do another square and go back to the theta squared model through the dual isogeny, and this gives you doubling formulas. And that way you recover the doubling formulas I showed earlier. And the cost is obviously 2 times 2 times the 2 isogeny. So now to compare, because for arithmetic, we compare to Montgomery, so for 2 isogenies, we will also compare to Montgomery. I did not explain the codomain cost, but this is what we get for image and doubling. And something similar to what happened with the ladder, it's image are faster in theta squared than Montgomery, but doubling and Montgomery are faster than doubling in theta squared. And codomain are faster, but by 1 addition, they're almost the same. So we could do hybrid 2 isogenies with the same kind of conversion we did earlier. But one issue that arises is that when you want to do arithmetic on Montgomery model and arithmetic on the theta squared model, you don't have the same constants to do your arithmetic. So the cost of your codomain gets bigger because you have more constants to compute, to do arithmetic on, to do images on one and doubling on the other. You need all the constants, so you have bigger codomains, and that's where we would be losing to chaining for isogenies on Montgomery curves, for instance. So this is not faster for chaining formulas, but it could be possible to do hybrid 2 isogenies. And the thing I'm interested in now is we've seen Montgomery curves, we've seen theta models, and they share a lot of similarities that I try to show, and these similarities are part of the Kummer lines. Theta models and Montgomery and Kummer. Well, on Montgomery curves, we introduce Kummer lines. Theta models correspond to other Kummer lines. So how do we have a more general background framework to work with Kummer lines? And this is what I will introduce in the end of this talk. So first, why are Montgomery curves and theta models so similar? Is because so if sorry. On Montgomery curves, what we did, we forgot about the y coordinates, so we just sent xyz to xz. And this is a map. This map is a degree 2 covering. So what that means is that if you take a point and you want to see how to get this point, you always have minus p and p, except for the two torsion, except when minus p is equal to p. So this is a two torsion. And this is also the ramification points of the map. So I wrote them down here, and I added an asterisk to the point that correspond to the origin. So 1, 0 is the point. The origin is set to 1, 0. This is what happened in Montgomery curves. And on theta models, if you take the map, you add this map from E modulo plus or minus 1 to the projective line. And if you get if you just compose it with the projection from E to E mod plus minus 1, you also get a degree 2 covering with other ramification points. But you still have 4, like in Montgomery case. And on theta squared model, don't do the details, but it's the same thing. And especially on theta squared model, as you can see, the ramification points are the same. Actually, if you wrote alpha equals a squared over b squared, because this is projective, the point a squared b squared correspond to alpha 1 and b squared e squared to 1 alpha. The only thing that changes is what is the origin. So you have the same ramification points, but you don't have the same origin. And that's why we had conversions from theta to Montgomery, which only differed by a two torsion point. Because what you do is just a permutation of the two torsion. What you wanted to do is just a permutation of the two torsions, so the origin is on the correct point. That's why they relate so well. And so now on to what is really a Kummer line. So every time on every previous model, we had this degree 2 covering. pi. And so this is what is a Kummer line. It's just a degree 2 covering of P1 with exactly 4 ramification points. And one of these points is marked. So this is the origin. The pi of the origin on the elliptic curve is sent to what we call the mark point, and what I noted with the small star. And some properties, interesting properties about that is that these ramification points are enough to describe the Kummer line. So we only need to study these. They are always the two torsion, and because of that, pi minus 1 pi p is always minus pp, except when both of them are equals. So yeah, the important information about that is if we want to know a map between Kummer lines, we only need to look at how it behaves on the two torsion. And this is what we'll be doing, and what will be the the general algorithm I will describe later. So some example, the example I will work on is this one. It's almost Montgomery. You have because we want two isogenies, we assume there is a two torsion point, so we put this X factor, because every curve with a two torsion point, you can, up to some homographies, you can send the two torsion point to the coordinate 0, 1, and the infinity to the coordinate 1, 0, so to the point at infinity, the usual point at infinity. So you can write the canonical example will be this kind of curve. And I don't necessarily want the full two torsion, so maybe this alpha is not in my base field, but in some extension. And the notation I will be using is the following one, so O, T, R, and S, which correspond to the 4 two torsion points and the ramification points. So these are only the necessary points I need. And there is only one small remark. When you have a model with O, T, R, and S, if you multiply gamma by a square, you still get the same. If you multiply gamma by a square, you still get the same two torsion. You're still on the same Kummer line, because multiplying gamma by a square corresponds to the isomorphism where I send xz to lambda xz, and this preserves the origin is sent to the origin, t is sent to t, and then you just have a new alpha. But if you multiply alpha by a constant lambda, you multiply gamma by a lambda squared, and it's still the same curve. This will be useful in some next slide. So now what I want to do is I will describe the algorithm of how to compute two isogenies, because this is what I want to talk about. And what we see is that two isogeny is with a kernel T. It's invariant because T is in its kernel. It's invariant by a translation by T. And conversely, if I have a degree 2 map which is invariant by a translation by T, I can build a two isogeny that way. So that's if I have such a map F, I can build J equals F minus F of O, so to ensure that G of O is equal to O. So I will be looking so the idea will be to look for maps that are invariant by T. And how to do that? So first we need to describe what is a map, what is a translation map on the Kummer line. And what we know is that it is an homography. So on our example, if I start with my two torsion O, T, R, and S, and if I want to know tau, I know that tau of O is equal to O plus T, so it's T. T of T is T plus T, so it's O. T of R is R plus T, so it's S, and T of S is R. And you get that tau is just the homography xz sent to gamma z x. And with homography, one known fact is that you can always describe an homography by a matrix of PGL2. So here the matrix will be 0, 0, gamma, 1, 1, 0. And we will be using this matrix to describe the translation map. So yeah, MT is the associative matrix to tau. And by construction, because T is of two torsion, if you just do tau squared, you get P plus T plus T, so it's just the identity. So MT squared is also equals to identity in in PGL2. So with the lift, you have a small constant called lambda T, which we called the type of T, and it's well defined up to a square. This is because of the previous remark on gamma earlier that only depends on the square. So, for instance, in the previous example, we had 0, gamma, 1, gamma. And if you compute MT squared, you get gamma times the identity, so the type is gamma. And one thing we will be using, so here we add lifts, and lambda T will depend on the lift. MT depends on the lift. But if you look at MT tilde over square root of lambda T, it only depends on T. The lift doesn't matter. And this is a matrix we will be using in the next section. So now we have a description of the translation. Next, what we want is a map in x squared, xz, and z squared that is invariant by T. So you can see this because we want a degree to map. So you can see this as a quadratic form. And because you want it invariant, you have this equation m times q. The action of m on q is equal to q. So the step 2 will be to compute the action of m on the canonical basis x squared, z squared, xz, and then build invariant quadratic forms from that. And we need 2 of these because we want 2 isogenous coordinates. So how do we do that? On the example, we start again with our ramification and our type. We take this matrix M. The action is the following. So on x squared and z squared, it's not invariant, but x is already invariant. And to build another invariant, you can, because m squared is equal to identity, you can just build x squared plus m, the action of m on x squared. And this is another invariant map. So that way we recover 2 invariant maps. And if we have those, u and v, which are not collinear, you can set f to be which end xz to uxz and vxz. And by construction, this map will be invariant by T. So is that enough? Not really, because with the previous example, you get that you only get 1, 0 and minus a1. So you only have 2 torsion points at the end, and you don't describe fully your Kummer line. So how can I get the remaining 2 torsion? It will be via 4 torsion, which I show on the next slide. Yeah, to recover a good shaped Kummer line, because 1, 0 is cool, minus a1 not much, but it's on case by case. And I do a description of Montgomery curves after that. So yeah, the idea is how you can recover. You already have 2 torsion points with what we did, but you need 2 others. And I go a bit quick on this one, but you can compute what will be the 4 torsion. What should be the 4 torsion point on the Kummer line with the equation 3 times t prime. If t prime is a 4 torsion point above t, 3 times t prime is t prime plus t. But it's also equal to minus t prime because it's 4 torsion. And because you're on a Kummer line, minus t prime is equal to t prime. So we can do chain equations like that, and you find some possible. You only find the 2 points that could be the 4 torsion points. And from that, because t prime and t double dash are above t, their images are 2 torsion points on the Kummer line, which will be the remaining one. So for instance, now I'm going to talk a bit about new formulas and especially the case of Montgomery curve. So in our Montgomery curve, you add gamma equals 1. And the first thing I want to talk is if you have a curve with complete two torsion, you want to compute the isogeny with kernel T1. So T1 is 0, 1. And you know the two torsion, the fourth torsion above T1. And if you do every step like previously, first you compute the translation by T1, it's just the simple map. Then you find some invariant quadratic forms. These two are working and they are not collinear. And then you build F with the previously found quadratic forms. You compute the images of the points. So you get 1, 1, 1, 0, 0, 1, and A2 squared, B2 squared. But so you have 4 torsion points as expected, but you don't have a Montgomery shaped curve like in the O1, T1, R1, and S1. So to go back to a more convenient form, you only multiply the x coordinate by B2 and the z coordinate by A2. And if you do that on the 4 two torsion point, you'll get a Montgomery shaped Kummer line. So yeah, that's pretty much what we do. We have a translated two isogeny formulas for the kernel with kernel T1, which were not known, I think. And you can compute them in 2 squared and 2 multiplication. So that's a bit better than what we could do in Montgomery. And if you change that with the dual isogeny given by this formula, you can recover the doubling formulas because almost doubling formulas. You get doubling formulas up to a 2 torsion point, and it's in 4 multiplication and 4 square like we had previously. So this is the first use case. You can get doubling formulas with that. You can't change them because we add T1 as a kernel, and now our new kernel is but we translate by S2, so it won't be convenient to chain isogenies. But the second case is if you know a 4 torsion point above one of the additional ones. So for instance, you know 4 torsion above R1, we call it R1 dash. You can get similarly you can get 2 isogenous formulas with kernel R1 in the same manner that we did with the same algorithm. You just find 2 quadratic forms that are invariant. And what is nice with where did it work? Okay, I have to do it again. What is nice with compared to the previous formulas is that, so first you recover doubling formulas with the dual isogeny. And if the next kernel, if you want to chain isogenies, here our kernel was R1, and if the next kernel is R2, you don't care about the remaining translation because it will be in the next kernel, so it will cancel out when you chain 2 isogenies. And last thing is formulas that were known by DeFeo, Rao, and Pleu. If you don't have the extra 2 torsion on the Montgomery curve, so you only have O1 and T1, you already know 4 torsion above T1, and assume you know 8 torsion above T1 dash, for instance. So this is T1 tilde. You can get another Montgomery model O2. I don't know why. Okay. You can get another model with the following formulas, which is also in 2 squared and 2 multiplication. And the only issue is that you don't really have you need a permutation of the 2 torsion because it's not in the same order as previously, but if you want to do a correction, you only need that. So that's it. These are the formulas I wanted to show. We found 2 new formulas, and we also found like formulas that were already known. So I don't know why it broke, but okay. So, and as a conclusion, what is new is this more general framework of Kummer lines describing them by only the 2 torsion. And this gives new isogenous formulas. Plus, we have this we have this hybrid ladder that provides beta doubling if you're in some circumstances where you have small constants. And what I'm working on currently is writing the article on what I talked about, but also classifying this Kummer line, classifying elliptic curves based on the torsion properties of the Kummer line via a Galois representation. So when an elliptic curve will have a theta model or Montgomery form or things like that, and how to choose good curves for elliptic curve cryptography and elliptic curve multiplication. So thank you for your attention.
Thank you very much, Nicolas. Yeah, if there's any question, then as usual, just type them in the chat. Or just unmute even. Shout them out. So I think you're trying to say something, but the microphone is not working.
Is working?
Yes, now it's working. Yeah.
Cool. I was wondering if you want to do these, if you want to do 2n isogenies, like in SIDH or so, with your previous formulas. Do you have like an oversight how much it will cost if n increases? Because then you can do the same thing as the
I did some timing, so doubling. I could mix doubling and images. So with the same algorithm provided in the psych documentation, but the issue is that codomains were about 4 squares, so twice the cost. And because asymptotically, codomains, you have exactly n codomains to compute, whereas you have n big O or n log n doublings and images. So asymptotically, this should not matter, but in fact, log n is about log of if you take the biggest prime in the psych documentation, it's 751 bits. So you have log 751, and it's not that much. So in fact, the n log n is almost the size of n, and you have to pay for the codomain being twice long.
Yeah, I see.
Nice. There's also a question from Tomoki, which is, what do you think about odd-degree isogeny computations? Is it possible to be generalized?
So this method can be directly generalized, but yeah, I don't know if okay. I try to find this slide, but one thing that was important is to determine the tau translation. And we had that it was an homographic because T is a 2 torsion point, so this was necessary in that case. However, Damien have ways to compute other isogenies on Kummer lines. It is known how to do that, yes. But it's not directly the same. this algorithm.
Okay, interesting. Thanks. Yeah, Timothy also says thanks. I'm not sure if there are any more questions, then I guess we can as usual, we'll hang around a bit longer if anyone wants to have a small chat. Well, sorry, Klein, you will maybe going to say that. Klein, are you there? Oh,
For a second. So I didn't really get what you said.
no, I was just asking if you were going to say some words at the end.
Yeah.
Oh no, it's not working again. Man, you even brought a new microphone and everything. Well, I can just say again, thank you, Nicolas, for a great talk, and yeah, and yeah, fantastic talk, very pretty slides. In 2 weeks we'll have Luciano, I think. Yeah, Luciano giving a talk also on computing isogenies, this time 2 isogenies even, or this time it's two isogenies. So stay tuned for that. And then, yeah, thanks again, Nicolas.